How do we begin to search for life in the universe? To begin the search, you want to ensure you're searching in a region of the galaxy with minimal harmful energies. The center of the Milky Way is much more dense with stars in the outer region. Nearby supernova explosions are much more frequent, and the radiation would sterilize any planets with life in that region. Stars very close to the center of the galaxy would receive intense X-ray radiation from the supermassive black hole at the center of the galaxy, and life would be very unlikely to be able to develop in such an environment. Also, stars farther towards the edge of the Milky Way galaxy tend to be very old stars and have very few heavy elements, and so those stars would be less likely to also have planets. Stars within the habitable zone, shown here, other than O, B, or A type stars, since they live a relatively short lifetime, are the best place to start our search. Next, we need to know what stars would have the best odds for supporting life, so we should understand how star metallicity relates to life as we know it. Formation of different types of planets depends on how much metals are available where planets form. The metals astronomers refer to are elements with atomic numbers higher than 2, which is every element except hydrogen and helium. Analysis of Kepler planets and their stars has shown that rocky planets are twice as likely and gas giants are 9 times more likely to form around stars with higher metallicity. In a nutshell, metal-rich stars tend to have more planets, so we should begin the search there. Now we need to know how the habitable zone relates to the distance of a planet from its star. We know the key with a habitable zone is that a planet has to exist in a region at the proper distance from the star for the planet to have water remain in its liquid state. If not, water on the planet's surface would either freeze or evaporate. However, there isn't a constant habitable zone that can be used for every star. A star smaller than half the sun's size emits more red and infrared light. An exoplanet orbiting in that star's habitable zone would quickly become tidally locked to the star, with one hemisphere too cold and the other one too hot to support life. These red dwarf stars can also produce extreme flares that emit harmful X-rays and particles that can destroy a planet's atmospheres, oceans, and possibly any life. Basically, for low mass, cool stars, the region is closer to the star, and for higher mass, hotter stars, the region is more distant from the star. Once we have established that a planet is in the habitable zone, it is important to know what stage its host star is in, since stars do not maintain the same color or luminosity over their entire lifetimes. As the star ages, it will in general cool off a bit and become more luminous, and as its luminosity changes, the location of its habitable zone will also change. A fresh main sequence star is ideal in order to give a planet optimal time for life to form. Astronomers have confirmed 29 exoplanets less than twice the diameter of Earth with all the necessary ingredients for life previously mentioned using the Kepler Space Telescope. The telescope observed temporary and repetitive dips it saw in a star's light that might indicate that a planet was crossing between the telescope and the star. The bigger the dip in the star's brightness, the bigger the planet was relative to the star. The more frequent the dips are, the faster the planet orbits. The planetary transits were Kepler's way of finding exoplanets. From March 2009 to November 2018, the Kepler Space Telescope discovered a total of 2,682 planets and is the real answer for how we began our search for life in the universe. And these are my references.